3 minutes. Maybe someone. You visit us? Transients. Zero views. They disappeared. Time to start. Oops. Where am I? What am I? Today I would like to speak about one of the techniques to solve a transient problem. When you need to know what happens when you switch something on or something off. We speak on free component of transient. Most needed, it's a calculus of overvoltage, computational overvoltage, or when you deal with things like wave protection. It's a complex, tricky problem, not very easy, but solvable. One of the ways to perform transient calculus is to use Laplace transform. What's good with Laplace transform? It's a common form of Fourier transform. In the space of Laplacian transform, the derivative operation becomes algebraic. Integration becomes algebraic. So integral differential equations become what? Algebraic equations. Equations easy to solve. So if in real time you have some function of time, it will become an image of function of complex frequency in the space of Laplacian transform. Laplacian terminology talks about images. Resistors will remain resistors. Coils with inductance L will become complex resistance PA. Capacitors 1 divided by P. Again, it's a complex resistance. But that's not all. You need to respect energy stored in reactive elements. So coil can store magnetic energy, 1/2 of inductance raised square of current. To reflect it, you add EL from 0. What means current of 0? At the moment of computation. For capacitors, you add minus capacitor voltage divided by complex frequency. For mutual inductance, MCM. So you, in the space of Laplacian transform, your schematic will become schematics of complex resistance. Solvable, your schematic will be solvable with a simple technique of circuit solution. For example, with nodal voltage technique. What you will get? Solution, direct solution of network will yield you node voltages as a function of complex frequency or images of nodal voltage. Branch currents as an image. And here problem. You need to perform inversion or Laplace transform. Heard about in circuits theory? With residue. Numerical techniques to do it exist. One of them, you can take this one in the library, starting from page 333, is to substitute image with a role, and factors of the role can be found as, it's interesting, it's a special substitution to do so, as a binomial coefficients. So I will show how it's done in reality. I don't think it's probable you will solve such tasks. It's for they are rare tasks if you will really over voltage management. It's a complex area. It will be your problem, your task, if you work for compound constructing super high voltage lines, something like this, or you will deal with super high voltage equipment. It's in real life quite a rare task. But if you will get this point, believe me, you will be indispensable. Because over voltage professionals in over voltage calculus absolutely unique. But it requires hard knowledge of math. They are never easy. Okay. Let's philosophy and see something real. I have this network. 24 volts battery, switch will close time 0. Here, this resistance 200 ohms. Next, splits in two. Branch 1, 220. Capacitor of 5 microfarads. Here, I will take it. This branch, one second, I will. Second one, 510 ohms. Then microfarads. These two branches are coil of mutual inductance. These two branches are coupled with 10 millihenry mutual inductance. Inside, one moment. All inductance 955 millihenry. What's this? 9,55 millihenry. And all resistance of primary coil 6.52 ohms. For secondary one, 8.53, and self-inductance is 7.5 millihenry. Nice network, but oh yes. And here I have one branch, 2 kilo ohms discharge. Yeah, you definitely like this network. Question is what happens when I switch. If someone asks you to calculate this by hand, kill him. Yeah, if someone asks you to calculate this by hand, kill him. It's a month of work. We will solve it with Laplacian transform. First, I need to do here, I have a zero condition. Before switch is turned on, none of capacitor is charged, none of coil is a current. Zero condition. It's for simplicity. It's easy. So I don't need to care about charges of capacitors and magnetic energy of self-inductance of this coil. Okay, what I need to do? I need to put the schematic into my program. This will be my ground point. Then I need to assign numbers to nodes. I think 4 nodes is okay. I do not assign number to base node. It's not necessary. Next, I need to assign numbers to branches and directions. This will be branch 2. My capacitor will be branch 3. This will be branch 4. This branch 5. this capacitor branch 6. I assign numbers to branch 6. Next step, I will need to create a matrix of incidence, matrix describing this network. I will free some space. Here will be AMF. Oh, matrix. What the rule of this matrix? Nodes, branch. If branch in falls into node, you write -1. It falls from, you write 1. No connection, write 0. In my case, I need 1, 2, 3, 4, 5, 6. Here are my 6 branches. 1, 2, 3, 4 nodes. First matrix of incidence, or M matrix. Branch 1 inflows into node 1 and no more connection. Branch 2 from 1 to 2. From 1. Branch 3, 2 to base. There is no role for base node, for grounding point, it's not necessary. Next, branch 4, from 3 to 4. Branch 5, from 4 to base node. And wait. Branch 5 from 3 to base node. And branch 6 from 4 to base node. Here is my matrix of incidence. It describes network topology. What's going on here? VMI, something not right here. Where is my... come here. Oh, this is fine, this is fine, this is fine, except one moment. Except one moment. What we need this. Yeah, I'm ready to write my new. I will. What I can do? 26.1. I will. Easy my job. I will copy template from yesterday's lecture. It's a nice template, but it's wrong. It's for different network. Here, first, let's change this one. This one is for different network, but it will work. What I need? -1, 1, 4 zeros. 0, 0, 0, 0. Row 2. 0, -1, 1, 3 zeros. 0, 0, 0. Row 3, 3 zeros. 0, 0, 0. 1, 1, 0. And here 3 0 0 0 0 -1 0 1. Yes. Now resistance of elements. EMF 2565, I measured it. Resistance of first branch 200 ohms. Resistance of the second one 220. 3 is capacitor, not needed. This is for branch number. Okay, this is not needed. Here 510, but that's not all. Yeah, I need branch 5 equals to 2000. First it's capacitor of the branch 3. Yeah, so 3. Capacitor of the branch 4 is 10 microfarads, not 1. Yeah, this will be okay. Self-resistance of the primary winding of my mutual inductance, self-inductance of primary side, these are okay. Yeah, L mu, mutual inductance. Elements. Now, what's this? EMF matrix. How many branches I have? 6. 1, 2, 3, 4, 5, 6. This is not needed. EMFs by branch. Since I have DC source, image of DC source, its magnitude divided by complex frequency. If needed, page 334. of this nice book contains a big table of images. Now, this part here I need to put into one diagonal of that matrix is it's a matrix of resistance. It's square. Column corresponds to number of branch and row same number of branch. And at main diagonal branch own resistance. For branch 1 own resistance will be 200 ohms R1. For branch 2 it will be R2 plus own parameters of my it's 1. For branch 3 it's a capacitor 1 divided by complex frequency multiplied by C3. Yeah, by C3. Do you see what I use? Complex frequency if it exists. I'm writing inside the function. Later this function will be called multiple times. And complex frequency will receive its values multiple times at the nodal point of approximation. Next, branch 4. It's R4 plus ohm of my metal inductance. 5 again C5 what I'm doing what I'm doing why nobody protests? Not C5 but C6. And here should be R5 or do I have R5? Yeah, I have R5. Yeah, now I have main diagonal, but that's not all. My schematics contain mutual inductance. Mutual resistance are written if between, let's say, branch 1 and 2 is a mutual inductance, so PM should be 1, 2 and 2, 1 symmetrically. In my case, mutual inductance connects branches 2 and 4. So, for 2, where knob, second one, number 4. Oh, yeah. And here 10 millihenry, the output. Yeah. So I write it symmetrically. I have my function. But function for what? I need to use it. One moment. I will take this from yesterday myself. Here, what I have, number of approximation members, 15 is okay, this I can't play with this number far because it defines number of binomial coefficients, but binomial coefficients are growing very fast, so I will run outside of maximum number allowable by PC. 16, it's okay. This one, time of simulation. Numerically, I will calculate within limited time. I will not get ideal function as a time function as analytical. I will get set of values. So these values will be, okay, maybe for 100 milliseconds. Number of steps, maybe I will increase to 5,000. It's number of steps within this interval, within this 100 milliseconds. This one, sigma. This will take values of frequency. P divided by double T max is okay. Actually, you can play up to from 1 to 10 with factor. This can little improve quality, precision, but it's okay. Now, number of variables. How many variables do I have? How many nodes I have? 4. How many branches I have? 6. 4 plus 6 is 10, okay? And, okay, for them, 4 voltages. This point. I started with 0 condition. So I feel with zeros, it's simple. Then I will show what to do if not 0 condition. But I will start with 0 condition. Here, my function, remember, I wrote inside a function. My function will be called at a special crafted points. It's a special points where frequency is real. There is one problem. If you look deeper, in most points, your frequency is a complex. You need to calculate function from something complex. But in this kind of substitution, there are nodes, not network nodes, but special points on complex plane where frequency is real. It's a special crafted approximation. At this point, I can solve my network as I am in the space of classical electrotechnics theory. So at this special point, I've solved my network. This side obtains binomial coefficients. And here is solution. Isn't for complex frequency instead. Solution is for substituted value. Here is backward conversion. This point converts backward to time. And last one, voltage and currents and time, simple drawing of charts. Let's see what happens. Thinking. Oh, drawing starts. Appears what I can reduce my time. 100 milliseconds is to 100 milliseconds is too much. Please, no, for capacitor. second, I will adjust. A couple of things. Oops. Oops, oops, oops. 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 Oops, 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 oops. It's a stupid mistake, isn't it? I don't have resistance here. It's the same. It's the same one. It's a stupid mistake.
What was the mistake?
Yeah, because this resistance is 0. It's a mistake. Okay, for branch 5, it's false from position 1. For branch 4, in position 1. Second. Branch 4. From 1 to 3. This one goes. And branch 6 from 3 to nothing. And 5 goes from 1 to nothing. Yeah, it's a mistake. It's unsolvable. Okay. It was mistake. One here. This one. 1 0 1 here. 0 0 0 minus 1 0 1. Yeah. And I have, sorry, only 3 voltage and 9 variables. It was a stupid mistake. Oh, my branch currents, and what about my voltages? Oh, here are my voltages. My voltages. Oops, 1 second. My currents and my voltages. For on one view, one moment. Oh, here are my voltages. Let's check here. Number 1 rises, it's steady somewhere at 30 milliseconds. Second node steady at 30, and this one at 40, goes slower. Let's see them in reality. This appears to be my very nice set of voltages. And see, currents. Branch with capacitor. Current ends at 0 because capacitor charged and remain. Number 5, where resistance remains steady and same current flows through branch 1. Steady mode is current of branch 5. Others are dropped to 0. This 1 second, I will switch myself up. Okay, let's try to see what happens in reality. Very easy to connect here. Scope is at node 1. Slope. Oops, sorry. Here, voltage at node 1. Something familiar? Rise 10 volts per division, rise to 25 volts. Something close to the slope. Next one, node 2. Node 2 is at capacitor, 5 microfarad capacitor. Here is voltage at node 2. On what we expect? Voltage at node 3. Oops. This one. Maybe I can get 1 second. I will take second wire. Yellow one will be node. Okay, no, yellow one will be node 3 and blue one will be node 2. Yellow line node 3 and blue line node 2. Up 2, 3. Currents. It's currents. Now more complex trick. More complex task is to solve problem of disconnection. To solve problem of switch off, I need to put capacitor charges and coil currents. Here I'm a bit lazy. At infinite time when network is powered, there will be no coil currents. Will be only capacitor charges. And what they will be? These two resistors form a divider. So you have good knowledge in electrotechnics theory. What will be voltage of capacitor when switch is closed for a long time? Charge 2. How can I calculate? Where this line sits? What's the magnitude at this point? It's a free component, goes to its limit, it's enforced component. What is enforced component here? You passed electrotechnics theory basics. It's divider of this resistor and this one. What will be voltage? Voltage at node 1. In infinite time. Switch is closed for infinite time. Oh shit. Ground. Voltage.
So 200 and this is 280.
Yeah, this 2000. 200, 2000.
So voltage 10. What is the input voltage level?
25.
25. Level.
25 divided by R1 plus R2 and multiplied by R2. Yeah? Yeah. Earlier, here I had a shovel. Nice green shovel. For those who can answer such question, I show them a shovel. It's your future. Good green shovel. Now I left it in garage. I had one special, my own nice green shovel. Okay, let's try to convert this into solution of switch on. What kind of schematics we need to create? First, we design schematics for the moment when for what time of moment? Just after switch is open. Just after, in Laplacian idea, we need schematics for the moment just after switch is turned. When switch is turned, first branch will disappear. I will do a trick. I will replace R1 with 2S6, 2 mega ohm resistance. I don't want to redraw schematic, I just will put. Next, I need my, this matrix, it can be here, UC1 will be EMF multiplied by, not 2, it's R5, yeah? And divided by R10 plus R5. Correct? Correct. Current here will be 0. Now I'm writing here EMFs. First 0, 0 is 0. Second, here should be P multiplied by EL1. It's a second, third branch minus UC1 divided by P. Next, branch number 4. P multiplied by EL2 multiplied. But I don't have it. It will be simple 0. Number 5, no elements. Number 6, in my case I'm lazy, so it will be the same. Here I modified my network. In case you switch on, nothing. Initial conditions are 0. When you switch off, there will be no power supply EMF. But you need to reflect energy stored in capacitors and coils. That's why I modified my EMF matrix this way. Number 3, number 6. Number 3, number 6. Yes. That's not all. That's not all. Remember, I point this place and told these are 0 conditions. It's a starting point of my chart recreation. In my case, there will be no 0 values, but values of previous regime. I need to solve my network. What I will do? Look at my trick. I will copy my function of network solution. I will copy it and rename. Okay, I use O previously. But here I will do one trick. Do not show it to anyone. I'm writing p equals to 1 minus 3. I simply ignore what it was called width and substitute with something very low. What I'm doing, it's a kind of blasphemy. I will solve, I need DC regime. I will solve DC mode as a very slow AC because I need initial values. Now, where is my no where is my come here. One moment. Yeah. I need this part, but that's not all. That's not all, that's not all, that's not all. Why it's not all? Because zero. This is what happens before switch is turned. Here is very important. To understand one thing. Before and after. When I calculate energy stored in capacitors and coil, I need schematics before switch is opened. When I calculate transient itself, I need schematics after switch is opened. Okay, let's see what happens. Oops. I don't know what is R10 at F and O. Sorry. Actually, I don't need it. This is not needed. Run. Oh, sorry. Oh, here are my results. Voltages going down. I need to extend simulation time. One moment. Simulation time is too short. We don't see them complete. Where is my 50, 100 milliseconds. Okay, here are my voltages. Voltage go set 150. Whoa, whoa, whoa. Currents. Voltages, 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 voltages. Okay, I will 200 millisecond simulation time. Oh, here are my voltages. 1 second, I need to go here. Oh, yeah. Here are my voltages. Exponential drop from 24 to 0. And my currents. Let's check, will we see these voltages? Here they are. Yellow, voltage at node 3, blue, voltage at node 2. Agree with theory? $25 volts before, this should be multiplied by 5. And exponential drops to 0. I have solved switch on and switch off. Solving it by hand. You tried? Transients. It should be in circuit theory. Yeah? How? Successful? Yeah. See how easy it is. You just need to put schematics matrix. Of course now it's easier for me because I can copy paste for myself. But you also can do, I will put this example in a learning system. Solution is easy. Yeah, it's because I can use inversion of Laplacian transform. In Laplacian space, I have just classical AC schematics. Only question is numeric how to get results from space of Laplacian images into space of time. Can be done. Need more? Start reading this book from page 333. It is in library. It's available online.
What
Latvian, but you can feed online to any online translator. You have Latvian language course? Yeah. And I'm smile. Yeah. Where am I? What I need to do? I need to get first a learning system. And here, theory of signal editing on. Lecture 19.